Here's an uncomfortable truth. You can memorize every command in this entire course and still get destroyed in a real investigation, because commands without context are just noise you copied from somewhere. So before we touch a single tool, we're going deep on the operating system underneath it. This is Module 2, Linux Fundamentals. And I mean actually fundamental, not the 20 commands everyone pastes into a terminal, but the 4 things that explain why those commands work at all. By the end of this video, you'll be able to sit down at any Linux box on the planet and know exactly where to look, why a permission setting matters, how to read a script somebody else wrote, and how to make your own programs run automatically and safely. Let's get into it. This module covers 4 pillars, and I want you to notice the order, because it is not random. First, the Filesystem Hierarchy, where everything lives on a Linux system. Second, permissions, the rulebook for who's allowed to touch what. Third, bash scripting, how you automate all of this, and how you read a script somebody else wrote. And fourth, systemctl, how you make a program start on its own, restart itself if it crashes, and log everything it does. Notice the logic. You learn where things are, then who can touch them, then how to automate touching them, and finally how to make that automation run by itself. Each part builds directly on the one before it. And stick around to the end, because we'll also blast through a rapid-fire cheat sheet, a hands-on lab you can run yourself in a virtual machine, and a self-test to check what actually stuck. Quick note on how each part is built, because the structure itself is a memory trick. For every pillar, I'll start with a plain English analogy before a single command shows up. Then real, worked examples, never abstract syntax with no context. Then I'll call out the security angle, exactly how this connects to the offensive and defensive material later in the course. And I'll leave you a couple of self-check questions at the end of each part. Try to answer from memory before I give you the answer, because that little struggle is what actually makes it stick. And here's the single most useful study tip in this entire video. Come back to the recap near the end at the 24-hour mark, and again after a week, even if it's just for 2 minutes each time. Brief, spaced review beats one long binge watch for anything you actually want to remember a month from now. That is not motivational fluff. That is how memory consolidation works. Part 1. The Linux Filesystem Hierarchy. Here's the analogy. Windows gives you separate drive letters, C, D, maybe a USB stick shows up as Linux does not do that. Every single thing on a Linux system, every file, every directory, every disk, even your keyboard and your webcam, hangs off one single tree that starts at one root, written as just a /. Plug in a USB drive, and Linux does not hand it a new letter. It grafts that drive onto the existing tree at some directory, a process called mounting. Learn this one tree well, and you can find your way around any Linux machine on Earth, because the layout is standardized by something literally called the Filesystem Hierarchy Standard. Now, there are about a dozen directories you need to know cold, and the trick isn't memoizing 12 separate things, it's noticing they cluster into a handful of families based on what they're for. On screen right now is that grouping laid out visually. Broadly, there's the root itself, the family of command directories where your everyday programs live, the configuration family, the family of directories holding data that constantly changes, the user space family, home directories and root's own home, the installed software family, and the family of virtual, live system directories that aren't really files on disk at all, just windows into the running kernel. 7 small groups beat 17 unrelated names. Let's go through them one at a time, starting with the ones you'll type the most. Start with the root, just the / by itself. That's the top of the entire tree, every other directory is a subdirectory of this one. It's the anchor for every absolute path you will ever write. Next, /bin and /user/bin, think binaries, meaning programs. This is where the essential commands every user needs live, ls, cp, cat, grep. On modern distributions, /bin is usually just a shortcut pointing into /user/bin. Why does a security person care? Because a trusted command secretly replaced here is a classic rootkit trick. Attackers swap real binaries for trojanized ones that look and act normal but do something extra and malicious behind the scenes. Then /bin and /user/bin, the system binaries, meaning admin-only tools, fdisk, iptables, user add. If a regular user is suddenly able to run something in here usefully, that's worth investigating immediately. Next, /etc. And here's a fun bit of trivia. The backronym everyone actually uses is editable text configuration, even though that's not its official origin. Every system-wide configuration file lives here: the parsed file, the shadow file, the SSH daemons config, the sudoers file. This is the single most attacked and most audited directory on the entire box, because anyone who can edit the parsed file or the sudoers file can create their own backdoor account. Then /var, for variable data, data that changes constantly while the system runs, logs inside /var/log, mail queues, sometimes web content. This is where you go first in almost every incident response. /var/log is the paper trail. And /tmp, temporary files, scratch space for any process, usually world-writable, and often wiped on reboot. World-writable, combined with predictable file names, is a classic race condition and privilege escalation surface. /home holds one subdirectory per regular user, home/Aisha, home/Musa, that kind of thing. If you're investigating a compromised account, this is the first place you look for downloaded tools, saved credentials, or shell history. /root, notice the spelling, nos, is the root user's own home directory, deliberately kept separate from /home so root still has a home even if /home fails to mount. If you ever find a regular, non-root user poking around inside /root, something has already gone very wrong. /user stands for Unix system resources, not user, and that mix-up is the single most common misconception about this directory. It holds the bulk of installed software, shared libraries, and documentation. In a hardened system, this ought to be close to read-only, so unexpected new files appearing here are worth explaining. /opt is for optional software, self-contained third-party packages that would rather not scatter their files across /us. Vendor software and some commercial security tools like to install themselves here. Then we get to the virtual directories. These aren't really on disk at all. /proc gives you a live view into every running process's memory, open files, and the kernel itself, exposed as if it were a real file system. Incident responders read /proc/ the process ID to inspect a live suspicious process without ever touching the disk. /system is the modern interface to hardware, drivers, and kernel tunables. Similar forensic value to /proc, just more hardware and driver focused. /dev holds device files, every piece of hardware represented as a file, like /dev/sda for a disk, or the well-known /dev/null and /dev/random, which you'll see constantly once we get to scripting. /boot holds the kernel image and bootloader configuration. A modified /boot is a sign of a very low-level, very serious compromise. /lib and /user/lib hold shared libraries, code that the binaries in /bin and /spin depend on to actually run. Rarely touched by hand, but library hijacking attacks specifically target this directory. And rounding it out, /mnt is a conventional, normally empty place to attach a file system by hand, temporarily. /media is where USB sticks and DVDs typically get auto-mounted. And /srv holds data a machine serves to others, like FTP or web content, on the distributions that bother to use it. That's the whole map, a dozen or so names depending how you count the combined ones, but really just 7 ideas. Knowing where things live is only half the job, though. You need to actually move around this tree, so let's cover the commands. pwd prints the directory you're currently in. Dead simple, just type pwd. The ls command lists contents, add a lowercase l for long format, add another lowercase a to include hidden files, or a lowercase h for human-readable sizes, so as-l shows you everything, including hidden files, in full detail. cd changes directory, cd/var/log takes you straight there. 2 special shortcuts with cd. cd tilde jumps to your home directory, and cd - jumps back to wherever you just were. The tree command shows a directory as a visual tree. You may need to install it first. And find searches for files by name, type, permission, owner, and more. For example, find /-name, *conf finds every file ending in .conf anywhere on the system. A couple more commands worth knowing. Locate does a fast file name search using a pre-built index, so locate sshd_config is nearly instant, Just remember the index needs occasional refreshing with update db. The file command identifies what type of file something actually is, regardless of its name or extension. And which, or whereas, shows you which binary would actually run for a given command, and where it physically lives. 4 shortcuts are worth knowing cold, because you'll type them constantly. A single dot means the current directory, 2 dots means the parent directory, a tilde means your home directory, and a dash, used right after cd, means the directory you were just in. Here's a memory tip that will save you forever. Read a path like a sentence, left to right. /var/log/auth.log means inside var, inside log, the file named auth.log. You never need to memorize where a file lives, you only need to be able to sound out the path in front of you. And here's why this matters for security, not just trivia. In Module 15, Incident Response, you'll be handed a compromised box and asked to reconstruct what happened. 9 times out of 10, you start in exactly 3 places. /var/log for what the system saw, /etc for what was configured, and /home, or /root, for what a user, or an attacker acting as one, actually did. Knowing this tree cold isn't academic. It's the first 5 minutes of every real investigation. Alright, quick self-check before we move to part 2. 4 questions. Try to answer in your head before I give you the answers. Question 1. Which directory holds hashed user passwords? Question 2. True or false, /user stands for user. Question 3. Your incident response lead asks you to pull yesterday's authentication logs. Which top-level directory do you go to first? Question 4. Which single character means my home directory, usable anywhere a path is expected? Here we go. Question 1. /etc/shadow. Question 2. False. It actually stands for Unix system resources, not user. Question 3. /var, specifically /var/log. And question 4. The tilde character. If you got 3 or 4 of those, you're in great shape for part 2, because permissions is where this course gets serious. Part 2. Permissions. If part 1 was the map, this is the rulebook, and I'd argue this is the single most important topic in the entire course. Linux was built from day one to be a multi-user system, many people and many processes acting on their behalf, all sharing one machine without stepping on each other's toes. Permissions are what make that possible. Most of the privilege escalation techniques you'll practice in Module 11 come down to one thing: a permission that somebody set one notch too loose. Let's read a real permission string. Run -l on any file, and you'll get a line like this: a dash, then rwx, then r-x, then r-, then a 1, then a username, then a group name, then a file size, a date, and a file name. Every piece of that means something specific. The very first character tells you the file type. A dash means a regular file, a lowercase d means a directory, a lowercase l means a symbolic link. The next 3 characters, in our example, read, write, execute, are the owner's permissions. The next 3, read, dash, execute, are the group's permissions. And the final 3, read, dash, dash, are everyone else's permissions. Then you get the number of hard links, the owning user, the owning group, the size in bytes, the last modified date, and finally the file name. Now here's something that trips people up. The same 3 letters, R, W, and X, mean different things depending on whether they sit on a file or on a directory. On a file, read lets you view its contents, write lets you modify or overwrite it, and execute lets you run it as a program or script. On a directory, though, read lets you list what's inside it. Basically, run ls, write lets you create, delete, or rename entries inside it, and execute lets you actually enter the directory with cd and access things inside it by name. And here's the pitfall almost everyone hits the first time. A directory with read permission but not execute permission lets you list file names with ls, but you cannot cd into it, you cannot open anything inside it, and you can't even confirm a specific file exists at that path, no matter how well you already know its name. You need the execute bit on every single directory along a path to reach the file at the end of it. Say that one over in your head, because it's the kind of thing that costs people 20 minutes of confused debugging. Now, typing out rwx by hand every time gets old fast, so there's a numeric shortcut. Each permission has a weight. Read is worth 4, write is worth 2, and execute is worth 1. Add up whichever letters are present in each of the three groups, owner, group, other, and you get 1 digit per group. 3 digits total, and that's the number you hand to chmod. On screen, you can see exactly how that works. The string read-write-execute, read-execute, read-dash breaks into 3 groups, each letter's point value stacks up underneath it, and the 3 totals come out to 7, 5, 4, chmod 754. Let's lock in the full scale. 0 is no permission at all. 1 is execute only. 2 is write only. 3 is write and execute. 4 is read only. 5 is read and execute. 6 is read and write. And 7 is read, write, and execute, everything. Now let's talk about actually changing permissions. Chmod 750, followed by a file name, uses the numeric form. The owner gets 7, full read, write, execute. The group gets 5, read and execute, and everyone else gets 0, nothing at all. There's also a symbolic form. Chmod u plus x, comma, g minus w, comma, o equals, followed by the file name, where u, g, o, and a pick the class you're changing, user, group, other, or all, and the plus, minus, or equals sign adds, removes, or sets permissions exactly. To change ownership, chown, alice:devs, followed by a file name, changes both the owning user and the owning group in one shot. Add a capital -R to apply it recursively across an entire directory tree. And if the owner's already correct and you only need to fix the group, chmod devs, followed by the file name, does just that. One more piece that explains why new files never start out wide open. There's a umask value that gets silently subtracted from a default every single time something new is created. New files default to 666, new directories default to 777, and umask, commonly 022, gets subtracted from that. That's exactly why a fresh file usually lands at 644, and a fresh directory lands at 755. Type umask by itself to see your current value, or umask 027 to set a stricter one for the rest of your session. Let's watch this happen in a live terminal. Here's the sequence. First, touch, notes.txt creates an empty file. Running us, -l, on it shows read-write, read-dash, that's 644, the standard default for a fresh file. Now watch, chmod 640, notes.txt, and run us, -l again. Now it reads read-write, read-dash. The group's permission dropped from read to nothing, and everyone else lost their read access entirely. That's 640, owner reads and writes, group reads only, everyone else gets nothing. Then chown, alice:security, notes.txt swaps the group over to security, and the permission bits themselves don't change at all, only the ownership does. That's the entire lifecycle: create, inspect, restrict, reassign. Now, 3 special permissions that go beyond the basic 9 bits. First, SUID, set user ID. A SUID program runs with its owner's privileges, not the privileges of whoever actually launched it. That's exactly why the parsed program works. It needs root's power to edit the shadow file, even when an ordinary, non-root user runs it on their own account. And here's why this matters enormously for your later modules. That same mechanism, a program running as its owner instead of its caller, is one of the most common Linux privilege escalation techniques you will deliberately exploit later, in Module 11. Find a SUID binary that lets you read, write, or execute something it shouldn't, and you've escalated from a regular user all the way to root. The defensive fact and the offensive technique are the exact same fact, just looked at from 2 different directions. Remember that phrase, it's going to come up constantly through this course. SGID behaves the same way, but for a program's group instead of its owner. On a directory specifically, SGID does something different and genuinely useful. Every new file created inside automatically inherits that directory's group, exactly what a shared team folder needs. And the sticky bit, seen mainly on shared directories like /tmp, means only a file's owner, or root, can delete or rename it, even though everyone can write into the directory it sits in. In numeric terms, SUID adds a leading 4 in front of your normal 3-digit permission number, and shows up as a lowercase s in the owner's execute slot. SGID adds a leading 2 instead, showing an s in the group's execute slot. And the sticky bit adds a leading 1, showing a lowercase t in everyone else execute slot. Two commands you'll use constantly, in real audits and in Module 11's own exercises: find, /-perm, -4000, then redirect errors to devnull, that lists every SUID binary on the box. And the same command with -0002 instead finds every world-writable file. Last thing for this part, sometimes owner, group, and other just isn't granular enough. You need one specific extra person to have access without changing the file's group entirely. That's what access control lists, or ACLs, solve. GetFacl, followed by a file name, shows the current list, and setFacl, -m, u:/bob:/rx, followed by a file name, grants the user Bob read and execute access without touching the classic permission bits at all. Good to know it exists, you don't need to master it on day one. Quick self-check for part 2. Question 1. Convert read-write-execute, read-execute, read--- to its numeric form. Question 2. A directory shows D, read-write-execute, read-execute, read-execute. Can someone in the files group create a new file inside it? Why or why not? Question 3. What privilege does the SUID bit actually grant, in one sentence? Question 4. Which single command lists every SUID binary on a live system? Answers. Question 1, 750. Question 2, no, the group only has read and execute, and creating a file requires write permission on the directory, which the group doesn't have. Question 3, it runs the program with its owning user's privileges, not the privileges of whoever launched it. And question 4, find, /-perm, -4000, -typef, redirected to devnull. If SUID and the Octal system feel solid, you're ready for the fun part, actually automating all of this with Bash. Part 3, Bash scripting. Bash, short for Born Again Shell, is two things at once. It's the thing you're typing into every single time you run a Linux command, and it's a full programming language for stringing those commands together. Here's the rule of thumb. The moment you catch yourself running the same few commands in the same order more than twice, that's Bash telling you it's time to write a script. Every script starts with a shebang line, #!, /bin/bash, and this absolutely must be the very first line in the file. It tells the kernel which interpreter should run everything below it. After that, chmod +x, followed by the script name, makes it runnable, and /, followed by the script name, actually runs it. And notice the callback to part 2 here. A script will not run, no matter how correct the code inside it is, until its execute bit is set. Permissions and scripting are not separate topics. They're the same system, viewed from two different angles. Variables are set with a name, an equal sign, and a value in quotes, critically, no spaces around that equal sign, and you read them back with a $sign in front of the name. Bash has no real data types. Everything is just text unless you explicitly force arithmetic. Double quotes allow variable expansion, so a greeting inside double quotes actually inserts the value. Single quotes are completely literal. The exact same greeting inside single quotes prints the $sign and the variable name exactly as written, with no substitution at all. And here's a pitfall that has broken real production systems. rm, $file, looks completely harmless. But if that variable happens to be empty, or contains a space, or was built from input you didn't fully control, that unquoted command can do something you never intended, delete the wrong thing entirely, or split into arguments you never wrote. Writing with the variable wrapped in double quotes is not a style preference. It's the difference between a script that's safe against weird input and one that isn't. Quote every variable every single time, unless you have a specific reason not to. Command substitution, a $sign followed by parentheses around a command, runs that command and drops its output right where you wrote it. Prefer this modern form over the older backtick syntax, which is harder to read and doesn't nest cleanly. A handful of special variables are worth memorizing cold. $0 is the script's own name. $1 through $9 are positional arguments, the first, second, and so on, word passed to the script. $hash, a $sign followed by the pound or hash symbol, tells you how many arguments were passed. $@ gives you all the arguments, each kept as a separate word. $? Holds the exit status of the last command. 0 means success. and $$ is the process ID of the script itself. And a handful of redirection operators control where output goes. A single greater than sign sends output to a file, overwriting whatever was there. Two greater than signs appends instead of overwriting. A less than sign reads input from a file. Two greater than sends error messages to a file. Two greater than &1 sends error messages to the exact same place as normal output. And a single pipe symbol sends one command's output straight into the next command's input. Conditionals follow the pattern. If a condition in square brackets, then the word then your code, optionally elif for more conditions, optionally else, and finally the word phi to close it out. Prefer the double bracket form over the older, POS-exportable single bracket form whenever you can. Double brackets avoid surprise word splitting and support pattern matching directly. A handful of test operators are worth knowing cold. For comparing numbers, -eq for equal, -ne for not equal, -gt for greater than, -lt for less than, -e for greater or equal, -le for less or equal. For comparing strings, a plain equals sign, or exclamation equals for not equal. -z checks that a string is empty, -n checks that it's not empty. -f checks that a path is a regular file, -d checks that it's a directory, and -e just checks that a path exists at all, regardless of type. And -x, -w, and -r check whether a path is executable, writable, or readable, literally part 2's permissions, tested from inside a script. Loops come in three shapes. A for loop, for, a variable name, in, a list, then do, your code, then done, or a C-style version with double parentheses if you prefer counting with an index. A while loop runs as long as a condition stays true. And an until loop runs until a condition becomes true, basically the mirror image of while. Functions are defined with a name, empty parentheses, an opening curly brace, your commands, and a closing curly brace. You call them just by name. Use the word local in front of a variable inside a function so it doesn't leak outside that function. And use return, followed by a number, for a numeric status between 0 and 255, not for actual output. If you want real output from a function, just echo it, and capture that from whatever called the function. Exit codes are simple. 0 means success, anything else means some kind of failure. $, checked immediately after a command, captures its exit code, and the word exit, followed by a number, sets your own script's final code for whatever calls it next. A handful of companion tools show up constantly, and you should recognize every one of them on site, even before you've mastered them individually. grep searches text for a pattern. Awk processes text column by column. SED finds and replaces inside a stream of text. Cut extracts specific columns using a delimiter. Sort and unique order and deduplicate lines. WC counts lines, words, or characters. And zargs turns a list of lines into arguments for another command. Let's put all of this together and read an actual, real script, one that ties parts 1, 2, and 3 together in a single file. It audits a directory for exactly the two things we just flagged in part 2, SUID binaries and world-writable files. And it writes the results to a timestamped log file inside /var/log, part 1's location for exactly this kind of data. Here's what's happening, line by line, in the script on screen. Line 1 is the shebang. Without it, the kernel has no idea this is even a bash script. The line that reads target directory, in curly braces $1:// means, use the first argument if 1 was given, otherwise default to the root directory. That's a compact, extremely common bash pattern worth recognizing on site. The log file line uses command substitution, $, parentheses, the date command with a format string, dropping a timestamp straight into the log's file name. Notice the very first line that writes to that log file uses a single greater than sign, and every line after it uses two greater than signs. Create the file fresh once, then append for the rest. Getting that backwards is a classic bug that quietly erases your own results every time the script runs. Both find commands are exactly the audit commands from part 2, SUID binaries and world-writable files, now wrapped in a script you can run anytime instead of typing by hand. And that redirect errors to devnull you see after each find command is part 1's devnull in its single most common real job, silently discarding the permission-denied noise from directories you can't read, instead of cluttering up your results. 2 good habits before you ever rely on a script like this for real. First, run shell check, followed by the script's file name. It's a free static analysis tool built specifically for Bash, and it will catch the unquoted variable mistake we talked about earlier, plus dozens of others, before any of them cost you anything. Second, get in the habit of starting real scripts with set pipe fail. It exits immediately on any error. It treats an unset variable as an error instead of silently becoming empty text, and it makes an entire pipeline fail if any command inside it fails, not just the very last one. Not every quick one-off script needs this, but reach for it by default, and only drop it when you have a specific reason to. Quick self-check before part 4. Question 1. What is the very first line of a Bash script required to contain? Question 2. After running a command, which variable holds its exit status? Question 3. $file versus with the variable in double quotes. What's the practical difference, and why does it matter? Question 4. In the script we just read, what does that curly brace, $1, pattern mean, in plain English? Answers. 1. A shebang line, !bin/bash, telling the kernel which interpreter runs the rest of the file. 2. $? 3. Unquoted, $file is subject to word splitting and glob expansion, so a value with a space or a wildcard can make the command do something you never intended. Quoting it treats it as one single, literal value, full stop. And 4. Use the first argument if one was given, otherwise default to the root directory. You now know enough Bash to automate almost anything in this course. Let's move to the last pillar, making programs run on their own. Part 4, systemctl. Every Linux process that has ever run is a descendant of exactly one process, PID1, the very first thing the kernel starts. On essentially every major distribution today, Ubuntu, Debian, Fedora, ACL, Arch, PID1 is systemctl. It decides what starts at boot, in what order, what restarts automatically if it crashes, and where all of that activity gets logged. Why did systemctl replace the old init system? The old approach, called systemctl, ran a strict, numbered sequence of shell scripts, one after another, waiting in line. Systemctl starts independent things in parallel instead. It can delay starting a service until something actually asks for it, called socket activation. It replaces those numbered scripts with explicit dependencies between units. And it funnels logging into one unified place, the journal, instead of every daemon inventing its own log format and location. Everything systemctl manages is called a unit, and there are several types. A .service unit is a single long-running process or daemon, think SSH.service. A .socket unit is a network or inter-process communication socket that can start a service the first time something connects to it. A .target unit is a named grouping or synchronization point, system's modern replacement for the old numbered run levels. A .timer unit is a scheduled trigger, system's modern alternative to, or companion for, cron. .mount and .automount units manage file system mount points as units. A .path unit triggers when a watched file or directory changes. And a .device unit represents a piece of hardware the kernel has exposed. Where these unit files actually live connects straight back to part 1's file system map. /user/lib/system/system holds the defaults shipped by installed packages. Don't hand edit these, because changes vanish on the next update. /etc/system/system is where your own units live, along with overrides of package units. This is where you work, and it takes precedence over the package defaults. And /run/system/system holds runtime-only units created dynamically. These are gone the moment you reboot. Now let's control these units with the systemctl command. Systemctl start, followed by a name, starts it right now. Systemctl stop stops it right now. Systemctl restart stops it, then starts it again. Systemctl reload asks it to reload its configuration without dropping what it's currently doing, if it supports that. And systemctl status shows the current state, recent log lines, and whether it's enabled. A few more systemctl commands. Systemctl enable, followed by a name, starts it automatically at every future boot, but notice, it does not start it right now. Systemctl enable, -- now, followed by the name, enables and starts it in one single shot. Systemctl disable stops it from starting automatically at boot. Systemctl mask hard blocks a unit. Even a manual start refuses to work until you unmask it. Systemctl daemon reload tells system to re-read unit files after you've hand-edited one. And systemctl list units --type equals service shows you everything currently loaded. Here's a distinction that trips people up constantly, so let's nail it down. Systemctl start affects right now. Systemctl enable affects every boot from now on. Neither one implies the other. Enable, by itself, will not start anything until the next reboot. And start, by itself, will not survive a reboot at all. If you want both, running now, and running on every future boot, either run both commands, or use enable with the --now flag to do it in one line. For reading logs, there's journalctl. Journalctl -u, followed by a name, shows logs for one specific unit. Journalctl -f follows the log live, exactly like tail-f. Journalctl -b shows everything since the last boot. Journalctl -p filters to error priority messages and worse. And journalctl -since, followed by a time in quotes like 1 hour ago, filters by time. Here's a security angle worth remembering. If /var/logs plain text files get cleared or tampered with during an incident, that's not necessarily the whole story. System's journal often keeps its own structured, binary copy under /var/log/journal, and that's harder to quietly edit than a flat text file. It's not tamper-proof against a sufficiently privileged attacker, but in modules 14 and 15, it's frequently the second place you check, right alongside the traditional syslog files. Now let's write your own service unit from scratch. On screen is a complete service unit file, broken into 3 sections. The unit section holds metadata and ordering. After equals network.target says, do not even try to start me until networking is up. That's an ordering rule, not a hard dependency. The service section is the actual how to run it part. Type equals simple means the command in exec_start is the process itself, and systemd considers the unit started the moment it launches, the most common type for a straightforward daemon. Exec_start itself is the exact command to run. Notice the script lives in /user/local/bin, part 1's conventional home for locally installed admin scripts, not /user/bin, which belongs to your package manager. Restart equals on failure, brings the process back automatically if it dies unexpectedly. And user equals auditor runs the service as a dedicated, unprivileged account instead of root. This is least privilege, one of the key principles at the very front of your entire course, applied directly to a running service. Finally, the install section is where this unit hooks into the boot sequence. Wanted by equals multi-user target means start me as part of normal, everyday multi-user startup. Deploying it is 4 steps. 1. Save the file inside /etc/system/system using your service name. 2. Run systemctl daemon reload, so systemd notices the new file. 3. Run systemctl enable --now, followed by the service name that starts it immediately and on every future boot. And 4. Run systemctl status and journalctl-if to confirm it's actually working. Quickly, on targets, system's modern replacement for the old numbered run levels. Old run level 0 is now poweroff.target, shut the machine down. Old run level 1 is rescue.target, single-user maintenance mode. Old run level 3 is multi-user.target, a normal, non-graphical, multi-user system. Old run level 5 is graphical.target, a normal system plus a graphical login. And old run level 6 is reboot.target, restart the machine. One more thing worth knowing exists, even though it's beyond Module 2, system supports directives that restrict what a service can do, even if it gets compromised. No new privileges equals true, stops it from gaining more privilege than it started with. Protect system equals strict makes most of the file system read-only to it. And private TMP equals true gives it a /TMP that no other process on the system can see. Keep these in your back pocket for when you start hardening real services later in the course. Final self-check for this part. Question 1. What's the practical difference between systemctl enable and systemctl start? Question 2. Which command shows you the log history for one specific service? Question 3. What did multi-user.target replace from the old init system? Question 4. In the example unit file, why does user equals auditor matter more than it might first appear to? Answers. 1. Enable effects every future boot and doesn't start it now. Start effects right now and doesn't survive a reboot. You need both, or the enable now shortcut, to get both. 2. journalctl -u, followed by the name. 3. Numbered run levels, for example, run level 3 or run level 5. And 4. It applies least privilege to a running service. If that script is ever compromised, the attacker inherits an unprivileged account's access, not roots. That's all 4 pillars. Now let's see them work together in one single story. Here's one small, coherent story that touches all 4 pillars at once, the kind of thing you will actually do on a real job. Imagine you're setting up a small monitoring script on a Linux box. You write it and save it in /user/local/bin, part 1, exactly where locally installed admin scripts belong, not /user/bin, which is reserved for the package manager. You set its permissions with chmod 750, and you hand ownership to a dedicated service account instead of root. Part 2, least privilege in action, not an afterthought. The script itself is written in bash. Part 3, reading whatever configuration it needs from /etc, and writing its findings to /var/log, part 1 again. And finally, you wrap the whole thing in a systemd.service unit, part 4, so it starts automatically at boot, restarts itself if it crashes, and has its output captured centrally where journalctl can find it later. Notice what just happened. Every single pillar from this video showed up in one ordinary task. That's not a coincidence, and it's really the whole point of this module. These 4 things aren't 4 separate subjects you memorize in isolation. They are one connected system, and once you see the connections, you stop forgetting the pieces. Before we wrap up, let's rapid fire through everything, because hearing it a second time, in a denser format, is exactly how it sticks. This is intentionally repetitive, lean into that. File system, in brief, the / is the top of the tree. Bin and userbin hold everyday commands. Spin and userspin hold admin-only commands. Etc. holds system-wide configuration. var holds logs and other changing data. TMP is scratch space, usually world-writable. Home holds regular user directories. Root is root's own home. Ursa holds installed software and libraries. Opt holds third-party, self-contained software. Proc and system are live, virtual process and kernel information. Dev holds device files. Boot holds the kernel and bootloader. Lib and userlib hold shared libraries. And MNT and media are for manual mounts and removable media. Permissions, in brief, 0 is nothing, 1 is execute, 2 is write, 3 is write and execute, 4 is read, 5 is read and execute, 6 is read and write, 7 is everything. Chmod 750, or the symbolic equivalent, changes permissions. Chown /group changes both owner and group. Add R for recursive. CHRP changes just the group. SUID is a leading 4, an S on the owner slot. SGID is a leading 2, an S on the group slot. Sticky is a leading 1, a T on the other slot. And your 2 audit commands, find, -perm, -4000, -typef for SUID binaries, find, -perm, -0002, -typef for world-writable files. Bash, in brief, every script starts with the shebang, hash, exclamation, /bin/bash. $1 through $9 are positional arguments, $@ is all arguments separately, $hash is the argument count, $? is the last exit status, $0 is the script's own name, and $$ is this process's own ID. If then elif else fi handles conditionals, for, while, and until handle loops, and functions use the word local to keep variables contained. Systemd, in brief, start, stop, and restart act right now. Enable, with the now flag, start something immediately and on every future boot. Disable stops autostart, mask hard blocks entirely. Status shows current state and recent logs. Daemon reload picks up hand-edited unit files. And journalctl, -u, -f, follows one unit's logs live. 4 pillars, 1 page, seconds to scan. Save that recap, come back to it tomorrow, and again next week. Here's your homework, and I mean that seriously. Reading about chmod and having actually typed it against a file that wouldn't budge until you got the bits right are not the same skill, and the second one is the one that shows up on the job. Do this inside a virtual machine, not your daily computer. 9 steps. 1. Boot a Linux VM. Ubuntu server is the friendliest choice for a first pass, and confirm you're at a shell prompt. 2. Explore the tree. Run nurse-la on the root directory, then cd into at least 5 of the directories from part 1, running ls inside each one, and write down one thing you find that matches what we covered. 3. Create a scratch area, make a directory called lab inside your home folder, then move into it. 4. Practice permissions. Touch a test file, check its default permissions, then change them with both the numeric and symbolic forms of chmod, checking ls-l after each change. 5. Create a scratch directory and safely try the special bits on something you own, SGID and the sticky bit, confirming each with ls-ld. 6. Write a small script with a shebang, a variable, and one find command from part 2, make it executable, and run it. 7. Wrap that script in a system.service unit, following the part 4 template, place it in the system directory, reload the daemon, and enable it with the now flag. 8. Confirm it worked, check systemctl status, then check journalctl for that unit, to see its output in the journal. And 9. Don't skip this one, write up what you did in 3 or 4 sentences and save it somewhere you'll find it again. Future you, 10 modules from now, will not remember the details unless you do this right now. Pause the video, go do this in your VM, and come back when you're done. That's the Linux pillar of Module 2, covered properly instead of skimmed. This same module now asks you to pair it with Windows, the registry, services, Active Directory basics, PowerShell, and macOS, its security model, gatekeeper, xprotect, to complete the full picture of operating system fundamentals, before Module 3 moves you into networking. 2 ideas showed up constantly in this video, and I want you carrying them forward deliberately instead of letting them fade into background noise. First, least privilege. In every chmod that didn't just default to 777, and every service that didn't just default to running as root. And second, you cannot defend what you do not understand. The exact mechanism behind a SUID misconfiguration is the same fact whether you're the one locking it down, or, later in Module 11, the one exploiting it on purpose. If this helped the fundamentals click, drop a comment with your self-check score, I read every one, and subscribe so you don't miss the Windows and macOS half of this same module. See you in the next video.